Okay, folks, Mr. Edwards again. Let's talk about this concept of energy. First, let's think about what it takes in order for you to, buy a new car or a new iPhone. You need money, and I want you to think of energy as kind of being like the same thing. It's a currency, but it's a currency that is not in paper form. There's no coins involved, but everything in the world, everything in our solar system, everything in our universe uses energy. So just like money is used to pay for everything that you do, energy is even more important because it allows you to do everything that you do, from breathing to your heart beating to the sun burning to a wind being created, etc. So energy is the ability to do something and to do work, and there's a physics definition for the word work. So work means to apply a force over a distance. So your muscles do work on your bones and on your body so that you can apply a force over the distance. If there's no force, well, there's no work being done. I mean, that makes sense. You don't apply a force to a chair, it's not going to move. If, on the other hand, you apply a force, or you try to apply a force to something big like a wall, and it moves no distance, well then anything that has a force multiplied by zero distance is going to have no work done to it. So again, energy is something that has the ability to get work done. Okay. There's two overlying types of energy, and ultimately we're going to talk about the different forms of energy. You're familiar with all these. Don't get too hung up on the words here because this is all more common sense type stuff. You just got to remember for right now two words. The first one is potential energy. This is the energy stored within an object. Okay, so I want you to think of a clothespin. If you squeeze a clothespin, it opens up. If you let it go, it's going to close. If you are into archery like I am, I have a compound bow. I pull it back. You've seen a bow like in the movies, and maybe you've used one before. It bends down. As soon as you let go of that bow string, the bow is actually going to be doing work on the arrow. Why? How does that arrow move? First of all, it needs energy in order to move. Where's the energy coming from? From the bow. The bow is storing the energy that I put into it in order for that arrow to actually do the work ultimately on the target. Okay, so this is the work of non-moving objects. This is the energy stored within an object, and that could be due to a couple different factors we'll talk about. So potential energy is stored energy. Work is not being done. It's stored, waiting to be used. The second type of energy is kinetic energy. The energy an object has as a result of being in motion. So if the object is moving, then it has energy. Depends on how much energy, or depends on how big it is, how fast it's moving. Both those variables will determine how much energy it has. And if you think about, I don't have one, but there's the Kinect device that you can use for your, I don't know if it's the PlayStations or whatever. There's a reason why they call it the Kinect, because it's using your moving energy in order to control the gamer or the game console. So this time work is being done. So up here you've got potential energy. This ball has the ability to do work or to start moving. Okay, it needs energy in order to do that. So once this ball is pushed to a certain point, it's going to release that energy. How is it moving down? Well, it's moving down because ultimately the earth and the gravity is being, the energy is being stored within that ball, put in by this guy right here. And then as soon as he releases it, that energy is being converted into moving energy. So first it's stored energy, then it's moving energy. So there's a fancy equation for calculating potential energy. Potential energy is nothing more than the mass times the gravitational acceleration, which in pretty much all the situations that we're going to be using is 9.8 meters per second squared. That's how fast the gravitational pull is on Earth. If you went to another planet or if you went outer space, well, then that would be completely different. In fact, if you were in true space and you had no gravity, well, then all of this would be equal to 0, because anything multiplied by 0 would be 0. And the height of the object. Now, there's other ways of calculating potential energy. For example, a spring. A spring doesn't function depending upon its height. It depends on how much it's actually coiled or pulled back. Okay, that's another equation. We're not going to worry about that. That gets into a little bit more tricky calculations that we don't want to deal with at the moment. So the potential energy is measured in these things called joules. And if you took all of these units and you combine them together, you would get these really fancy, long, complicated units that we just affectionately abbreviate as joules. So the shorthand for this is potential energy, PE, mass, M, gravity, G, and then H is height. And then, oh, I didn't put down the shorthand. The shorthand for potential energy would be a capital J. So potential energy can be affected by height, because I'm going to go back for a second. If you have an object that's being pulled down like that ball and it's at a certain height, well, the ball's going to have more potential energy the higher up it is. And if you take a look at these two balls, this ball, but at 4 different heights, okay, or you can look at it as 4 different balls, 4 different heights. The higher an object is, the more potential energy it has. This is pretty easy to understand. You put a ball a little bit above the ground, you drop it, you're going to hear a little thunk. Okay? As you get higher and higher up, you're going to hear a louder thunk. Well, the ball is doing work on the ground, and then ultimately there's work being done on the air to produce the sound. So the higher the ball is, the higher the sound is, or the louder it'll be. So therefore, the more energy the ball has, the higher up it would need to be. So that has the least potential energy, that has the most. Where did the energy from the ball come from? I picked it up or you picked it up. That's where it ultimately came from. The ball isn't going to just magically get this energy. It has to come from somewhere. And there's a way to explain energy in the universe, and that energy is neither created nor destroyed. It is just recycled. So it ends up getting converted from one form to the other. So for example, this kinetic energy converted into sound energy, and other types as well. We'll get back to that. Let's say you keep the height the same, so that ball was being dropped from, or different masses, or objects are dropped from the same height, but they're different masses. So this could be like, I'm just going to give you an example here. This could be like a ping pong ball, this could be like a golf ball, this could be a bowling ball, this could be a big huge boulder. So if you think about it from that perspective, the more mass an object has, the more potential energy it has. You know, drop a ping pong ball on your head, no big deal. Drop a golf ball, ooh, that hurt a little bit. We're not going to drop a bowling ball on your head, but you get the idea. You know, you would definitely feel it more. Again, if you did sound, you drop these, you get a little tink there, a little bit more, a little louder, you know, until you get a big bang. So less potential energy. Why? Because it has less mass. Most potential energy. Why? Because it has more mass. And if we go back to that equation, mass is one of the 3 variables for potential energy: mass, gravity, and height. So if we keep all the others consistent, but we increase the mass, you get more energy. Where's the energy come from? Well, the more mass an object has, the more gravity pulls on the object, just because every little piece of matter is being pulled by gravity, so therefore gravity is pulling more because the object has more mass. Okay. So believe it or not, you could take something like a bowling ball and you could have a golf ball. Those 2 objects can have the same amount of energy, even though the bowling ball is obviously much bigger. So if the bowling ball is 20 times more massive than the golf ball, then you would have to take the golf ball and lift it 20 times higher. So if this were 1 meter, this would have to go up to 20 meters. in order for those to be the same. So it's pretty neat that you can get the same amount of energy out of two totally different objects as long as you're playing around with that variable of height. Okay, moving energy. So if the object's not moving, it's potential energy. When it is moving, that's kinetic energy. So potential, oh, that says the wrong thing. That should say kinetic energy, so I made a little mistake there. Okay, so, but this is all the other stuff is the same. 1/2 the mass times the velocity squared. So this tells you that you have to have a moving object. So again, that should say kinetic energy. If you have a moving object, this will be anything, you get a kinetic energy of anything greater than 0. If this were not moving, well then what's your velocity? What's your speed? 0 meters per second. Well, anything times 0 is 0. Okay, so you have to have a moving object. This is abbreviated by KE, kinetic energy, 1/2 the mass times the velocity squared. A little caution here on calculating this. What I've had people do is they've taken 1/2 the mass times the velocity and then they square it. That gives you an incorrect answer. You need to take the velocity first, almost do it in reverse order. Take the velocity, square it, then multiply these. It's going to make a huge difference. So be careful on calculating. So once you have objects in motion, they have a certain amount of kinetic energy. So let's take, for an example, these two cars here, two of the same exact cars. One is traveling a little faster than the other. Okay? The car on top has more kinetic energy because it's moving faster. Okay? Physics is common sense stuff. If I take a snowball and I just kind of toss it at you, in the winter time when we're goofing around, well, it's just going to kind of bounce off you, no big deal. If I take that snowball and you whip it at you, or your friend is whipping a snowball at you, you're going to feel it more. Why? Well, because the same snowball thrown at a much, much greater speed is going to be hurting more because it has more energy behind it. Okay, now if we have two different vehicles, one really, really big, one really small, and they're both traveling at the same speed. Well, think about it. If these were in a crash, or they hit a brick wall or another vehicle or something like that, the one that has more mass is going to have greater amount of damage associated with it, to the objects that it hits and to itself, etc. Because this object here has more kinetic energy, even though it is traveling at the same speed. Dump truck has the most, the little car has the least. Okay, is it possible for the two objects to have same kinetic energy if their masses are different? Absolutely. And you could probably already guess how we're going to achieve that. The little car has to go faster. So this is making the assumption that if the big dump truck is 10 times more massive than the little car, so 10 times more mass than this guy, then this has to be traveling 10 times greater. So 10 times 10 would be 100. So this one's traveling 10 times faster. The kinetic energy would be the same. Keep in mind too, this is important, does not take friction into consideration. A lot of these are ideal situations and they don't take into consideration when you're dropping a ball, ping pong ball versus a bowling ball. It's assuming the air resistance isn't going to be a big factor. Okay, potential energy, this is just review. Potential energy is affected by height and mass. Gravity too, but if we're here on Earth, you're not going to have to worry, you don't have to worry about that. So as height increases, potential energy increases. As height decreases, the potential energy decreases. So an object doesn't have as far to fall, so it's not going to have as much energy that is stored in it when it's at a lower height. Kinetic energy is affected by speed and mass. So if you increase the speed of an object, the energy increases. If you decrease the speed, the kinetic energy decreases. Notice mass is a factor in both. As mass increases, both potential and kinetic energy increase. As mass decreases, both kinetic and potential energy decrease. Notice that there's these inverse relationships. Speaking of inverse, think of a seesaw. You're going to see me doing this in class with my hands. This would be like my body. This would be my arms out, right? And I'm moving my arms up and down. Ideally, in a perfect situation, if you measured potential and kinetic energy, potential energy should equal kinetic energy. That's when everything's all said and done. What you have at the start for potential energy is going to be what you have at the end. So if you notice this potential energy here, so potential energy is stored. So this is an example of an object that you've raised up off the ground, and it has potential energy. It's not moving. It's not moving, so it has kinetic energy way down here. This is supposed to represent like 0, okay? But a lot of potential energy. As soon as you let that ball go, what happens in slow motion is that you've got potential energy being converted into kinetic energy. So this starts to go down. Why? Because it's being used, that energy is being used for motion. This one starts to increase. They get to a point where they're equal, and then eventually potential energy drops down so that there's no more potential energy. You've used it up. This is like your gas tank that's empty now, and you're moving as fast as possible. So all of that has been converted to kinetic energy. Again, this is in an ideal situation where no other energy is lost to any form other than just the movement. So this is an inverse relationship. So as you have one that's increasing, the other one is decreasing, and vice versa. Here's a situation where you've got a car that is way up high, and this explains this inverse relationship. So the kinetic energy is, so first of all, potential energy, this blue line, is way up here at the top. So as soon as that object's up at the top, bang, all blue. No kinetic energy. Why? Because the object is not moving. Okay, so all the energy is in potential. Once the car is let go, now it starts converting down. It's always, the energy is always 100%. The question is just where does it go?